Alright, so in the last video we started learning about the definite integral, and I probably could have combined the last video and this video all into one video, but I thought it might help to break them up into as small chunks as possible. Really all I'm going to do with this video is kind of expand upon this new idea, this definite integral, by looking at a different example. So here's a different example. Pictured is the graph of y equals negative 1/2 times the absolute value of x minus 3 plus 4. It's this kind of weird V-shaped graph. And what we want to figure out with no context or English or anything is this huge mess. And hopefully from the last video, you're able to read this and you see this integral sign, so you're thinking the area below the curve. What curve? The curve y equals negative 1/2 times the absolute value of x minus 3 plus 4. Exactly what's pictured here. So I want the area underneath this curve in red, meaning between the curve in red and the x-axis, from x equals negative 3, right here, to x equals positive 3, over here. Well, the good news, if you watched the last video, is figuring out this area is no harder than it was in the last video. Maybe you kind of view this as a rectangle and a triangle, and you figure out the area of this rectangle is 6, because it's a 6 by 1 rectangle, and then you figure out the area of this triangle is 9, because the base has length 6 and the height is 3, and 1/2 times 6 times 3 is 9. So the total area pictured in red here is just 15. That's it. Evaluating this definite integral at this point in the class is just a geometric argument for how much area there is shaded in here. Great, let's move on. What if we were asked to evaluate this definite integral? Well, it's not really any harder, and you might wonder why I keep asking you these questions. Trust me, there's a punchline here eventually. The area from 3 to 7, here's 3, here's 7, underneath the curve, negative 1/2 x minus 3, absolute value plus 4, same curve that's shown. Evaluating this definite integral is just figuring out how much area is shaded in green. We can again do the rectangle triangle argument. Let's see, we got a rectangle here that is 2 by 4, so it's got area 8, and we got a triangle here that is 2 by 4, so it's got area 4. 8 plus 4, I believe the area shaded in green is 12. What do we got next? Another definite integral. You're like, dude, I'm getting the point of these. Why do you keep telling me to do these? Well, look, there's a bit of a punchline here. Think about what this question is asking you. It's asking you to evaluate the integral from negative 3 to 7 of negative 1/2 absolute value x minus 3 plus 4. The area underneath this curve from negative 3 to 7. This question is asking me to find the area outlined in blue. And if you're the least bit clever, you might recognize that the area in blue is made up of the area in red and the area in green. And since the area in red is 15 and the area in green is 12, the area outlined in blue must be equal to 27. If you had just done these two parts, you could figure out this part pretty easily just by adding these two guys up. And even if you hadn't just done these two, you could have evaluated this from the start just by drawing various rectangles and triangles and such. But it's certainly easier if you already knew these two answers. The fact that this integral is equal to this integral plus this integral is fairly obvious when you draw the pictures, but it's a lot less obvious when you just see it in an algebraic context. And that's this general conclusion that I'm talking about here. It'll be really useful for you to know that the integral from a to b of some function f of x dx is the exact same as the integral from a to c of that same function f of x dx plus the integral from c to b of that function f of x dx. All right, when you see it written this way, it's like, whoa, that's really complicated, and that looks like a formula that I'm going to have to try really hard to memorize for our class. But it's not if you think about it in terms of this picture. Think about c as some number in between a and b. And if I want the area under the curve from A to B, what I could do is figure out the area from A to C, and then pick up from C to B. And the thing that's kind of cool about this is this holds true even if C is not in between A and B. So even if C is bigger than B, for example. If C is bigger than B, this integral would be really weird, but we learned in the last video how to deal with cases like that. So this rule ends up being true even in the case that C is not between A and B. But I think it helps to remember it by thinking about the case when C is in between A and B, when really all we're doing is figuring out the area outlined in blue by first figuring out red, then figuring out green. Easy enough? Okay, cool. Let's do another integral. Evaluate the integral from 3 to 15 of negative 1/2 times the absolute value of x minus 3 plus 4. Okay, it's the same curve from 3 to 15. Let's go up here to our picture. We now want our left endpoint to be over here at 3. I'll try to reuse this picture a little bit. So we're ignoring the stuff in red. We want all this stuff in green, but we want to go really far all the way over here to 15. Wait a minute, this is going to be really weird because we've been thinking about the integral as the area below the curve, bounded by the curve and the x-axis. And that works out fine for this shaded region, but how are we going to figure out this shaded region? Is it as simple as just calculating the area in this weird like bluish purple color? Does the fact that the curve is below the axis make any difference? Short answer is yes. To figure out the area in pink here, it's really easy. Do the same thing you've been doing. Recognize that you got a triangle, that the length of the base of that triangle is 4, and the height of that triangle is 2, and the area of a triangle is 1/2 the length of the base times the height. So 1/2 times 4 times 2, so 2 times 2, or 4. We already figured out that the area in green was 12, and the area in red is 15. We've now figured out that the area in pink here is 4, but what about this area over here? I mean, if you just figure out the area of the triangle, you'll get the same area you got up here, right? Through symmetry. It's the same triangle. The length of the base is 4, and the height is 2. So half the base times the height, again, gives me 4. But it feels different because when we define these definite integrals, we've talked about the area below the curve above the x-axis. And that doesn't happen here. This area is above the curve and below the x-axis. So how do we talk about that area? You're like, yeah, you don't have to keep restating the question. Tell me the damn answer. All right, I'll tell you the damn answer. It's just negative. We talk about this area as -4. And yes, I know negative area doesn't really make sense, but if you allow the area below the x-axis to count as negative, then we can continue to use this analogy of the area under the curve when we're figuring out integrals. So to answer this question, the definite integral from 3 to 15 of this same function, what we could do is think about 3 to 15 as the green area, the pink area, and this dark blue area. We could say that this integral is equal to the integral from 3 to 7 of -1/2 absolute x minus 3 plus 4 dx, plus the integral from 7 to 11 of that same function, plus the integral from 11 to 15 of that same function. We're really taking advantage of this general conclusion that we talked about earlier in this video, that if you're trying to find the area under the curve from 3 to 15, what you could do is find the area from 3 to 7, and then add to that the area from 7 to 11, and then add to that the area from 11 to 15. This integral we already figured up here is equal to 12. This integral in pink we figured out right here was equal to 4. And even though it's a little bit weird, this final integral from 11 to 15 of this curve, because we're below the x-axis, we count the area as negative. It's equal to -4. The final answer, if somebody asked you to evaluate this integral right here, it would just be equal to 12. One more comment that I want to make before I end this video. The integral of this same curve from 7 to 15 is something that we already know, right? From 7 here to 15 is this 4 and this -4. This integral is equal to 0. But if we didn't have this picture drawn up here, and all we had were the different answers that we've gotten to these questions in A and B and C above, I think we could still come to that same conclusion. How could you do it? Well, you could use part C to say that the integral from 3 to 15 is the exact same as the integral from 3 to 7 plus the integral from 7 to 15. And then you could be like, well, this is the one that I want for my answer, so let me just subtract this term to the other side. Kind of do algebra with these integrals. This integral here is this integral minus this integral, because you're subtracting this from both sides of the equation. And since we already know the values of each of these integrals, from 3 to 15, we figured out it was equal to 12, and from 3 to 7, we figured out it was also 12. Since 12 minus 12 is equal to 0, the value of this integral here must be equal to 0. You're probably running out of patience, but I want to show you one more thing here. This conclusion that we made up here, that we thought of as, if I want to figure out some big area, I can go from the start of the big area to some sort of middle-ish point, and then from that middle-ish point to the end of the big area, can also be used down here. We can go from the middle, loosely speaking, to the end by taking the area from the start to the end and subtracting the area from the start to the middle. Just like you can add up areas in the way that would make sense to figure out the values of integrals, you can also subtract integrals to figure out areas when you need to. This might feel a little bit elementary right now and not involve any calculus at all, but what you'll see are the fundamentals that we're learning in these sections will be super important. So being really comfortable with the notation and some of these properties, even if the properties are obvious when you're drawing the graphs, will be really useful because we're not always going to be drawing graphs. We're going to be doing this more and more algebraically as we go.